Welcome back, students. We are at section 17.7, entitled The Common Ion Effect and the Effect of pH on Solubility. So we've been discussing solubility and recognizing the fact that compounds like this are tied in equilibrium between their dissociated ions in aqueous solutions. And we're looking at silver chloride for this example. If you remember from our solubility rules, remember that we would call this an insoluble compound in water. And yet we're learning it does have a small amount of solubility in water, and its solubility happens to be 1.33 times 10 to the negative fifth moles per liter. So we can only dissolve that many moles per liter of solution. So the goals of this section, though, is to explain how common ion affects solubility, as in, if I have a solution of chlorine ions, will that affect the solubility of silver chloride? And also we're going to talk about how pH might affect solubility of compounds. So if we look at this compound and think, what if I have a solution over here of sodium chloride? So I have a salt solution. So what's in here? Well, there's Na plus and Cl minus in this solution of H2O. And I'm going to pose the question, is silver chloride more, less, same amount of solubility in the solution versus H2O, versus pure water? So we need to look and consider what's in this solution here. We have chlorine, which is a common ion in this equilibrium. So if there's a common ion between this solution and this equilibrium, then we have to consider Le Chatelier's principle. So Le Chatelier's principle tells us that if I add something on this side, it will push it to the left. If I add chlorine to this equilibrium, it should push it back to solid. So in this case, if I'm going to go ahead and add AgCl to this, I'm going to rewrite our equilibrium really quick. Aqueous, aqueous. Because there's a lot of Cl minus in the H2O solution, it's almost like we're adding chlorine to this equilibrium. So we are going to push left. So that means AgCl is less soluble in an NaCl solution. So that's what we mean by the common ion effect. It's basically Le Chatelier's principle with respect to the equilibrium of solid and aqueous solutions. So there's a practice problem in your book. Problem, let's see, what is it? 17.19. That does an equilibrium problem to actually calculate the molar solubility of HCl, considering a 0.2 molar solution of sodium chloride. So go through that problem, and it connects back to this idea. So that's the first part of this chapter. Now let's look at the second piece. Explain how pH affects solubility. Still thinking of Le Chatelier's principle here. So let's go down here. I'll just jot this down. How does pH affect solubility? Well, we need a situation where a common ion is involved in an acid-base equilibrium. So let's look at magnesium hydroxide for a second. So magnesium hydroxide, solid, the equilibrium with Mg2 plus, aqueous, plus OH minus, aqueous. 2 moles of that. So would pH affect solubility? It would, because if we look at one of the products here in the equilibrium, this is OH minus. So if we add H plus, we are going to form H2O and remove OH minus. Remember, if we remove something on this side, we're drawing the equilibrium towards this side, drawing it to the right. Le Chatelier's principle says if I add OH minus, or if I add magnesium, I'm going to push the equilibrium to the left towards products. But if I remove OH minus, I'm going to push it towards the right. So if I remove OH minus by adding H plus, I'm going to dissolve more MgOH2, essentially. It's going to be more soluble. And if I think of a more practical example here, let's think of me not being able to move this anymore. 1 second. It is not moving anymore for me. Technical difficulties here, guys. Good times. Hey, it's working. All right, we're back. We are back. We are recording this live, so we're going to run into some things. So let's think of a situation where maybe we have a statue. Or a monument. And it's made out of limestone, which is calcium carbonate. Okay, so I've got this surface of the statue. And let's suppose I have some rain droplets. Ooh, these are wonderful raindrops. You know what? We have the capabilities. We have the colors. We have the skills. And I'm forming some water on the surface. Just spectacular artistic skills, I gotta say. Why am I rewriting this? You know it's a statue surface. Okay, let's zoom in a little bit though on this water droplet now. So what's happening here? We have this is zoomed in. Let's pretend this is H2O. And perhaps this rain is slightly acidic. So maybe this is some water that it was up in the clouds. I know you're just getting all the art skills today. Believe me, I know I should record art videos. And there are pollutants. Bad, sad pollutants that get into these clouds. That can actually change the water vapor to produce acidic rain. So if now it's not just nice and neutral, we have H plus, and this is calcium carbonate. How might that affect the equilibrium? Well, let's go back to this equation. Remember, this is always going to be in aqueous solutions. This, very, very insoluble compound in water, typically. Water doesn't really affect this statue, this monument. It's not dissolving away. But it is still technically in equilibrium in aqueous solutions between this and this. Basically dissolved and solid calcium carbonate. So what happens if it comes in contact with our acid here? So now all of a sudden, H plus is involved in the equilibrium. So at the surface, this is an equilibrium, and H plus acid reacts with CO3 minus base. Even though there's not much there at the surface of the water, this is an equilibrium between dissolved but the tiny bit that's there, this will react. And by Le Chatelier's principle, that means we're removing carbonate from the equilibrium, and we're drawing this to the right. So little by little, we dissolve the statue. So that's why we want to be careful with adding acidic, bad pollutants in our rain on things like statues and monuments there, because of this common ion effect. Okay, that is pretty much everything I'd like to talk about for this section. Go through the practice problems in section 7.7 and I will see you on the other side for section 7.8. Talk to you guys later.